Now in this lecture we will discuss about electric field and the effect of electric field on the dielectric material of high voltage engineering. We will also try to discuss about electric stress control in high voltage equipment so that the breakdown of electrical equipment can be avoided. Now this lecture or this topic is extremely important as far as the electrical insulation or the design of electrical insulation of high voltage equipment is concerned. The electric field which is produced by high voltage electrode can be classified broadly into two categories. The one is say uniform magnetic field, other is non-uniform magnetic field. The non-uniform magnetic field is further classified into two categories. One is weakly non-uniform field and the other one is extremely non-uniform field. So these fields are represented in terms of a factor called a degree of uniformity or Schweiger factor. The Schweiger factor is 1 in the case of uniform field, whereas in the case of non-uniform field, this Schweiger factor, which is indicating the degree of uniformity, is less than 1. For say weakly non-uniform field, the Schweiger factor is greater than 0.25 but less than 1, whereas in the case of extremely non-uniform field, the Schweiger factor is even less than 0.25. So the electric field is essentially a gradient of applied voltage, which is simply voltage applied divided by distance between two electrodes. For example, these are the two electrodes and this is the distance d between two electrodes, and if the electrodes have a potential difference of V volt, then simply E is equal to V by D. In uniform field, the potential across the electrode changes linearly or it is distributed linearly. What it means is, say for example, this is the electric field in this across this electrodes. The potential across this space in which the electric field exists will be linearly distributed. That means at any point the electric field intensity will be constant, and there exist say equipotential lines, and these lines can be represented, say for example these are the electric lines of force, then the equipotential lines can be represented which are orthogonal to the electric field, and these lines forms a perfect square in the region between this main field. So electric field intensity is constant throughout this space. In uniform field, the insulation breakdown always takes place without partial breakdown. So if the field is uniform, then the breakdown will occur without any partial breakdown. Partial breakdown means there is a breakdown which is initiated at a certain point and then it spreads throughout the insulation. Also in uniform field, the breakdown voltage say VB is always equal to partial breakdown inception voltage. So our goal is to make sure that the electric field between two electrode is uniform and the degree of non-uniformity is not too high. So that will ensure that the dielectric medium between the two electrodes in high voltage equipment will not get damaged due to large electric field. So always during the design it is ensured that the electric field is well below the dielectric strength of or the breakdown strength of high voltage equipment. So this slide represents the typical electric field configuration. So for example, there is one electrode which is say spherical or say cylindrical, and this is another electrode, and there is electric field between these two electrodes, say electrode 1 and electrode 2. You can notice that all the electric lines of force, they are perpendicular to the surface from where they originate, and they originate in all direction. However, these lines travel towards the other electrode which is having say other opposite polarity, say negative polarity, if this is having a positive polarity. So all the lines will travel towards the electrode number 2, and you can notice that in this region the field is almost uniform, whereas electric field is non-uniform at other places. Say for example here or here, the electric field is not uniform. So if you consider this line, then the potential at any point will be same, and therefore the name is equipotential line. So in the region between two electrodes, say for example in this region, these lines forms a perfect square with electric lines of force, and therefore we can say that this region is having uniform magnetic. Therefore we can say that this is the region in which we have uniform electric field, whereas in this region you can notice that the equipotential lines and the electric lines, they do not form a perfect square. This is not a perfect square, and therefore the field in this region is non-uniform. So this is figure A represents the field between say sphere or cylinder and the plane. Whereas there is another figure, you can notice that there are 4 conductors. This is a cross section of bundled conductors. So this is conductor 1, conductor 2, conductor 3 and 4. And these conductors are of say positive polarity. Then you can notice that all the electric lines of force, they are perpendicular to the surface of these conductors. And here these lines repel each other because all the electrodes have same polarity. You can also notice that there are equipotential lines and they are forming the circle. So these are the lines, or equipotential lines means the lines such that on every point on these lines the potential will be same. So potential of all these points on the line is going to be same, and these lines are always orthogonal to the electric line. So this electric line and then equipotential line, they will be always perpendicular. So a uniform field can be achieved by two electrodes specially designed for a given gap distance with the help of these two profiles. So in order to get a uniform field, one must follow the profile of electrodes suggested by Rogowski and Borda. We will see later on how these two profiles can be represented. Now, the utilization of dielectric material is very important aspect in the case of high voltage equipment. It means that in order to give large breakdown strength to dielectric medium, we need to use large amount of dielectric material, but this will increase the cost of say high voltage equipment, and this will also increase the size of that equipment, and it is possible that this entire dielectric material is not properly utilized. That means there is excessive dielectric material in this equipment, and therefore this is not a good design of high voltage equipment. At the same time, it is also very important to note that the dielectric material should not be too less in a particular high voltage equipment, otherwise it will result into say partial breakdown and then subsequently complete breakdown. So therefore the utilization of dielectric material should be optimum. The value of Swagger factor eta, which represents the degree of uniformity in electric field, or it also represents degree of utilization of dielectric between two electrodes, is an important parameter. Higher the value of the Swagger factor eta indicates that the dielectric material is better utilized between the two electrodes which are separated by a distance d. So higher the value of say Swagger factor eta represents better utilization of electrode or dielectric material which is having a thickness d, or the distance between two electrodes is d, for a given actual maximum field intensity and better utilization of insulating properties of say dielectric. The value eta always lies between these two numbers, that is the degree of uniformity can be as high as 1, indicating the uniform electric field between the electrodes, and it can be as low as 0, indicating that the electric field is highly non-uniform. So the knowledge of this Swagger factor is very important for estimation of electric field intensity inside the dielectric. So the eta basically serves very good reference and an important information for optimum design of insulation of high voltage equipment. So when we apply voltage to electrodes, we create an electric field, and then the insulation which is under the influence of this electric field is stressed. So the whole idea is to better utilize the dielectric associated with high voltage equipment. So for the better utilization of dielectric, we want that the electric field is as uniform as possible. The ideal utilization is accomplished only when Swagger factor is close to 1, which is practically not possible, and therefore the design of equipment should be such that the value of Swagger factor is close to 1. More the non-uniform field, higher the electric stress in the dielectric at a particular location only, where the breakdown of dielectric may start. It is possible to achieve higher degree of uniformity by giving suitable shape and size to various electrodes in the equipment, and this is called stress control. So stress control in high voltage equipment is essentially giving a proper shape to different electrodes of an equipment so that the electric field will be uniform. The dielectric or insulator which is in the vicinity is highly vulnerable to breakdown. The electrodes must be given suitable shape at projecting edges. That means at sharp edges, a suitable shape should be given to an equipment so that the stress can be controlled or the breakdown can be avoided. So for stress control, electrodes are extended and form in such a way that higher field intensity than the main field will not appear anywhere in the dielectric. So the whole idea of stress control is to avoid the sharp points, sharp edges in the equipment, and to make the electric field as uniform as possible so that the possible breakdown can be avoided. So if we are talking about equipment, then this is the kind of equipment which is used in high voltage laboratory to test some apparatus for evaluating its insulation property, and the voltage which is produced by these equipments is generally very high. It's much higher than the equipment under test. When we talk about very high voltage, then corresponding electric field is also very high, and therefore high voltage laboratories are very tall because it is essential to make sure that there is sufficient clearance between these kind of equipments and the wall and the roof and the other structures in the lab, so that the stress or the electric field is well controlled. This is because if the field is not properly controlled, then this very high electric field produced by this equipment may produce a breakdown. So the figure on the right side represent an high voltage equipment. So the electrodes at high potentials in the laboratory are given large smooth dome like shape, which you can notice here, so that the electric stress on the atmospheric air can be minimized. The sharp contacts are generally enveloped by large diameter hemispherical electrodes having an aperture. So you can notice these situations where hemispherical structure is there and there is an aperture for doing any connection. Also, instead of wires, a tubular electrodes of large diameter are used for connections to bring down the field intensity to very low value. So you can notice here that there are tubular structures which are provided to produce a uniform electric field and to bring down the electrical intensity. You can also notice that there are toroids, and these toroids are essentially to produce uniform electric field. If the equipment is of very large size, then the trend is towards developing such an equipments by using a segmented electrodes. You can notice there are small segmented shapes here. These are very smooth and disc type structures. By combining all these small discs, a big structure, big spherical structure or toroidal ring or then hemispherical structure can be formed, and all these small elements of this high voltage equipment are worked out by using suitable optimization method, because the shape of all these small segments should be such that the resultant body is very smooth and it is able to produce uniform electric field in the nearby region, and then electric field is not concentrated, which may otherwise result into breakdown with nearby structure, that is with wall or with other equipment or with the roof. So in order to control the stress, it is essential to give a proper shape to the electrodes. If an electrode is, say for example, not having a proper shape, or if there is abrupt interruption of electrode or termination at either anode or cathode in high voltage engineering laboratory, then it may produce very large electric stress on the dielectric. That means it may be the air in the neighborhood, or it may be some kind of solid insulation. So the dielectric in the vicinity will become highly susceptible to the breakdown, and therefore to avoid this and to obtain higher degree of uniformity of such a fields, electrodes must be given suitable shape. So this is essentially a stress control which we discussed earlier also. So for stress control, in principle, the electrodes are extended and given a form or a shape so that higher field intensity than in the main field will not appear anywhere in the dielectric. And to achieve this, Rogowski suggested a typical profile in 1923 to design an electrode which can produce a uniform electric field in the region where it is required. Particularly, this profile is very useful in testing laboratory where the idea is to produce uniform electric field to test high voltage apparatus. So this profile, which is known as Rogowski profile, is very popular to design an electrodes. Now this slide shows two profiles. One is a Rogowski profile and other is a Borda profile. The aim of these two profiles is to produce uniform magnetic field and to avoid the sharp edges, sharp points where there is possibility of electric breakdown. So you can notice that this is one electrode and then this is another electrode. This is a ground electrode, for example, and this electrode is at certain voltage. It's at high voltage. So in this region both the electrodes are parallel and therefore the electric field is very uniform. Similarly, the equipotential lines are exactly orthogonal to the electric field and both forms a perfect square. So this is a region where the field is uniform or the electric field is uniform. While at edges, you can see here at edges the shape is given so that the electric field concentration can be avoided. You can notice that the electric lines of force, they are spread and they are not concentrated, and these sharp points can be avoided by this kind of smooth structure. On other hand, there is another profile which is a Borda profile, and according to this profile the electrode is given a typical shape so that the electric line of force are spread at the edges and the sharp corners are avoided. So both these profiles are essentially used to control the stress in high voltage equipments. Now let us consider high voltage bushing of a transformer, in which how the stress control is achieved. So in this slide you can notice that there is a typical transformer bushing, and it consists of a metallic tank which is at 0% potential, and there is a central conductor made up of either copper or aluminum which is at 100% potential. The conductor is further connected to power system, whereas the other end of conductor is connected to transformer windings. So there are two typical parts here. One is a conductor, other is a tank. In between these two there is an insulation. So this material may be a ceramic material or it may be an epoxy material. What is shown on right hand side is a situation where the stress control is not employed, whereas on left hand side the dielectric material in between, say, transformer tank and the conductor is having capacitive grading. This capacitive grading on left hand side is in the form of concentric cylinders, and these concentric cylinders helps distribute the potential uniformly along the length of bushing. These concentric cylinders are basically floating screens, and they are so positioned that the electric potential is uniformly distributed throughout the length. So essentially a capacitive grading is employed here as far as left hand side of this bushing is concerned. On other hand, there is no any kind of stress control which is employed on the right hand side of this bushing, as a result of which you can notice that the electric potential is not uniformly distributed. Almost 75% of this voltage is distributed across the half of the bushing, whereas remaining half of the bushing receives 25% voltage. It means that the electric lines of force are crowded in this region, and therefore this part of the bushing is under electric stress, and therefore it is quite possible that there may be some kind of breakdown in this region for not having employed any kind of stress control. So these are certain extended shapes of electrodes of high voltage equipments in which the stress control is employed. For example, say this is the right angle turn of bus bar in a gas insulated substation, where there are two bus bars, they are meeting, and there is a sharp corner or sharp edge formed here. So by providing a dome type structure at this sharp corner, the stress control is achieved because the electric field will be very uniform in this region, and then all the sharp corners can be avoided. Similarly, this is a stress cone on a cable end termination, where you can notice there is a cable end, and then this is a conducting material inside the cable, and there are two dielectric materials around this cable, and you can notice that this is a cone shaped structure which is added near a termination in order to avoid any crowding of electric line of force near the terminations, and the electric line of force can be spread. Similarly, this is a bushing of high voltage capacitor, where different dielectric materials are used to spread the electric line of force, and same as the case here, this is a bushing where again there are two different dielectrics. This is a dielectric constant of the oil, and this is a dielectric constant of the bushing, or say the insulation between the conductor and the tank. And here, as we discuss, the concentric foils are also used to provide capacitive grading. So these are the different methods of stress control which are used for minimizing the stress in a certain part of the equipment by reshaping the electrodes, or by either extending the shape of the electrodes.